By the end of this video, I'll expect you to know how to map an LDS to a relational database schema and some of the differences between an SQL database and a true relational database. This video is being made available early for students who already have experience with relational databases and are interested in understanding this mapping right away. For those of you who just want to focus on data modeling, I'll just ask you to get a general understanding of this material by the end of the course. First, a little about Structured Query Language, or SQL, also pronounced SQL. This is a database querying language and isn't the most exciting new language to be learning these days, but is still ubiquitous and solves problems really well. Some popular SQL products these days include MySQL and PostgreSQL, which are open source, free to use, and highly documented online. Also available and very popular are databases provided by Oracle and Microsoft. These are reputable corporations and they stand by their products. Here's an example of PostgreSQL code. The differences between this and other flavors of SQL are fairly minor. This code creates two tables, school and student, and inserts some data into the tables, including 2 schools and 3 students. SQL requires you to get down the nitty-gritty of data types like integer and variable character field. One point of interest is that this code also creates a foreign key reference. This says that for each row in the student table, the school ID needs to match one of the values in the school table. This ensures data integrity so that we can't have data mismatching between tables. Also notice that having a school ID on student means a student has exactly one school, but a school can have many students. Having inserted that data, we can execute queries to extract it again. You can see there are 2 rows in the school table and 3 rows in the student table. Each of these 3 students rows has a school ID, either 1 or 2, which is derived by referencing the school table, which offers school IDs 1 and 2. At the bottom, we can do a little magic using the inner join feature that uses those common school IDs from the 2 tables to combine or join the data from both tables into one resulting table. Each row of this result represents a student paired with their school. This is just to let you know the feature is there. No need to understand how it works right now. We'll be learning a lot more about joins later in the course. What I'd like you to understand here is how a student is a dependent entity of school, and the relationship between student and school is implemented as common data IDs on each table. This video will cover how to make a mapping between LDS and real data structures like this. But we're actually going to avoid working with SQL for 2 reasons. One reason is that the SQL code syntax and the data types are details that vary from product to product, and those details are not important right now. The other reason is that we'd like to get you thinking about a concept called a relation. What we've talked about is a relationship. Looks like this line that connects 2 entities. In this video, we're introducing a new concept called a relation, not a relationship. A relation is a data construct that we normally draw like a table with rows and columns. It comes with some special rules that make it more interesting than just a plain table. So just to reiterate, a relationship and a relation are completely different things. What we call a true relational database uses relations to store and represent data. Most people use the terms relational database and SQL database interchangeably. In this course, we're saying that SQL supports an approximation of a relational database. SQL tables are like relations, except relations require a primary key and therefore do not allow duplicate rows. This looseness might make SQL more flexible in some cases, but it also gives you some rope to hang yourself with. It opens up interesting possibilities for software bugs, and more importantly, the freedom to generate data tables without thinking about primary keys lets us get away with building software without thinking carefully about our data. Relations come with rules that encourage us to be rigorous and think about the data. The idea behind relational databases was pioneered in 1970 by Ted Codd at IBM and has been a subject widely discussed and studied ever since. Meanwhile, an SQL standard was developed, and many different products have been developed that implement SQL databases. There are some truly relational databases out there like RHEL, though perhaps none that perform well at scale. In the software world, we're realistically using SQL databases. But I encourage learning the relational theory first so that when you go out there and use SQL, you're using it more mindfully. We'll be talking a lot more about relations later in the course, but just a flavor here. Suppose we have 3 people and 2 of them have the same name, John Smith. If we do a relational reduce operation to get the person name, we will get a relation containing 2 unique names. If we do an SQL select, we will get a table with 3 names, including a duplicate, and no way to tell the duplicates apart because the ID column has been removed. SQL does support doing the distinct operation by applying a select distinct clause, but you have to remember to ask for distinct results. In a relational database, there is no way to get duplicates. Now that you understand the concept of relational databases, the rest of this video will cover a procedure for mapping an LDS to a relational database schema. This is a technique you can use regardless of what SQL product you're using, or possibly even if you're using a non-SQL product. An overview of the procedure is that we will map each entity, then each attribute, then each degree 1 link, and finally map our identifying descriptors. Let's return to this model we studied in the identification dependency path video. The ability to follow those paths is needed to perform this mapping. The first step is to simply map each entity to a relation. So our relations here are person, activity, location, region, action, landmark, and geographic area. Then we'll map each attribute to a column. Here's the format. For each relation, we'll write its name, then a colon, and then a set of columns on that relation. For example, this means the landmark relation has columns landmark name, historical description, and established date, because those were the attributes on the entity. Pretty simple so far. For the next step, we'll need to know how to follow a path of identification dependency, which we covered in an earlier video. Here's a quick review. The identifiers for independent entities are easiest to see. These entities have no bars on links. The identifiers comprise the list of identifying attributes inside the box. So the identifier for person is person ID, for landmark is landmark name, and for geographic area it's area ID. The other entities on this diagram are all either dependent, intersection, or subordinate. And all of those get part of their identifiers from other entities. It's easiest to start from the independent entities and work backwards along the dependency paths. The identifier for region is area ID. For location, it's area ID and location name. For activity, it's area ID, location name, and person ID. For action, it's area ID, location name, person ID, and action number. Another point worth reviewing is degree 1 links. Take a moment and look through this LDS. For each entity, how many degree 1 links does it have? I'll pause and let you count. Okay, so person has 0. Activity has 2. Action has 1. Location has 1. Landmark has 1. Region has 1. Geographic area has 1. So that's a total of 7 degree 1 links on this LDS. With all that review out of the way, we're ready for the next step in the process, which is to map each of those 7 degree 1 links. With one exception, we're not going to map the link from geographic area to region because it's not possible to map that one. At the end of the video, I'll ask you to try to explain why that is. The way we map is we look at the describing entity of the link. We describe a student by saying that the student has one school. In that context, we call student the described entity and school the describing entity. Knowing that, we want to gather the list of identifying attributes from the describing entity and its path of identification dependency, and then add those attributes as columns on the relation of the described entity. In this case, we're going to the describing entity school, gathering its identifying attributes, which is just school ID, and adding that school ID as a column to the relation for student. Returning to the previous data model, here's the result of that exercise. We've added columns to most of the relations. Do we understand these columns conceptually? Region is subordinate to geographic area. It is a geographic area. so it makes sense that we're adding an area ID to its relation. For each location, we need to remember its region, which we just said is an interpretation of a geographic area, so we also need an area ID there. For each activity, we need to remember its person and its location. And here are the identifying attributes for those. And so on for the activity of an action and the location of a landmark. The highlighted items here are typically mapped to foreign keys, but not necessarily. If moving to implementation, you might want to consider whether null values are allowed. Also, there are times when we want to allow values other than the ones listed on the foreign table, and that's a design decision that we won't get into in this video. The next step is to map primary keys on each relation based on the identifying descriptors of each entity. A primary key on a relation is very similar to the identifier on an entity. A primary key will be a subset of the relation's columns. For this exercise, we'll enclose primary key columns in square brackets at the beginning of the column list, as shown here for person. Here's what it looks like when it's complete. The columns and brackets should match exactly what we found earlier for the identifying attributes for each entity. Landmark is an interesting one to point out. We added the location name and area ID columns so we could remember one associated location. But those attributes did not contribute to the identifier for the landmark entity, so they are not included in the primary key for the landmark relation. The result of this exercise is a list of relations, each with a list of columns, including which ones should be part of the primary key. From here, it's a trivial exercise to map this all the way to SQL for anyone who knows the language, and there's plenty of documentation available for all the popular SQL databases out there. Now check your understanding.